think maybe everyone's here since it was exactly the right amount. This is about the Math Center, which perhaps you've heard of. It's in the library, and the Math Center is a place where anybody can go for extra assistance with math if you're working on the homework and don't have any friends to work with or whatever. You can try the Math Center, or if for whatever reason you don't want to talk to me. I mean, I'm always enthusiastic about helping out, but if you're just looking for more options, the Math Center is an option. You can see here the drop-in hours. That means you can just walk in there, or you can make an appointment if you want to be sure that somebody will be there. Sometimes you walk in and it's like kind of full, or maybe there's nobody there who knows about the material in this particular class, although everybody there should know calculus, so that hopefully won't be a problem. But anyway, you can make appointments there on the website. Anybody got any questions about that? It's run by some of our graduate students and upper level undergrad math majors, so I hope that that is helpful to you if that's something you're interested in trying. All right, great. I think it's time we can get started. I enjoyed reading your interesting things about me that you told me yesterday. Something interesting about this class. 2 different people of you said I am a twin, and one of you said I'm a triplet. Amazing. Yeah, that was surprising to me. It wasn't the most amazing thing I read was someone in one of my other classes said, I have a rock stuck in my face from when I fell as a kid. Yeah, that's something. I don't know who, because I don't know people's names yet, I don't know who said that, but I'm going to be looking very carefully at everyone's face. I assume you can't really see it, or else they would have taken it out. I don't know. I've never heard of that. I had one student once who had, I hope you don't mind a little story. He had really terrible handwriting. I'm used to some people have bad handwriting and whatever. I don't really care that much, but I just I couldn't read what he was writing, and I said to him once after class, I kind of feel badly complaining about people's bad handwriting, but I said I really have a hard time reading what you're writing sometimes, and he said, oh yeah, I'm really sorry about that. It's he held his hand up. He said, yeah, it's all since I lost that knuckle. And I was like, oh, okay. And then I was like, I have no idea what that means. I still don't really know. I'm sure that means something, but yeah, I didn't know you could lose a knuckle, but he lost a knuckle. He still had his whole finger though. It looked normal. There wasn't a hole, a void in the middle of his finger. I don't know. Anyway, I'm sorry to make light of the situation. If any of you have lost a knuckle, I'd be interested in hearing what that actually means. It's probably not funny to lose a knuckle. Let's talk. We are continuing our review topics. The first one on the big list was basic integrals and derivatives. And today I want to talk about the u-substitution, which is, I would say, considerably harder. Substitution. This is the basic, perhaps the only integral trick that I'm going to assume that you have some familiarity with. So I hope that you do know about integrating using the substitution. There are other integral tricks, but this is the only one that we do it in our Calc 1 class, so we assume that the Calc 2 students know about it. This is a trick for integrals based on the chain rule. And for the idea is to change the variable. That's why it's called substitution. You change the variable to make the integral easier. For example, if I'm looking at an integral that looks something like this, integral of 5x plus 2 all to the power 6. Those are parentheses there. Hold on. dx. All right. Now, this integral actually you cannot do directly, without doing any tricks. You can do this with the u-substitution, but without doing any tricks, you can't directly do this integral because it has this slightly complicated structure of this thing, this linear polynomial thing, inside of the 6th power, all right? And the fact that there's one thing inside of another thing really makes it so that you can't use any of your standard integration. The basic integral really is only capable of handling stuff added together. That's no problem. But anything else, any multiplications or stuff inside of another stuff, you got problems. All right, but in this case, the idea behind the substitution is, what about change the variables? I said the idea is to change the variable to make the integral easier. This looks like a 6th power of something. So instead of that, the idea is you make u, it's basically always called u, which is why it's called the u-substitution. There's no good reason to call it u. It's just what we usually call it. And if you make it that, then this turns into integral of u to the 6, and now that's easy, right? Because it's just a 6th power. Much easier. By much easier, I mean you can actually do that one. The other one is just like straight up impossible without doing some kind of substitution. But the u to the 6 is much easier. Now, the problem, there is a slight sort of technicality, and the issue is these are not actually equal to each other. This integral is not equal to this, like the answers are not the same. But there's a slight adjustment that you need to do to make it so that they are equal. So they're related, but they're not quite equal. And here's the idea behind this. If we were doing derivatives, if it was a derivative, then it would be, I'm talking about the derivative of this thing, 5x plus 2 to the power 6. The answer to do this derivative, you have to use the chain rule, and I hope you all remember the chain rule. The chain rule says you do the derivative of the outside part first, which would mean 6 here, and then you go 5x plus 2 now to the power 5, and then times the derivative of the inside, which in this example is 5. All right, that's the chain rule that I just did. You do the derivative on the outside, and then separately times the derivative of the inside. All right, that was the chain rule, and that is another, so the, let me just say, this is the derivative of the inside. So, doing the derivative of this, you have to additionally multiply times the derivative of the inside. If I wanted to do the antiderivative of that, which is what I see up here, right? If I wanted to do the integral of this, so for the antiderivative, the derivative of the inside must already be present. Because it's supposed to be the opposite of the antiderivative is the opposite of the derivative, right? So if you're doing the derivative, you get the answer by additionally multiplying times the derivative of the inside. If you wanted to do that in reverse, say look at the thing on the right and go backwards, you have to already have the derivative of the thing on the inside. It's already in there to begin with before you go backwards, all right? And this is the basic idea of the u-substitution. If you've done this before, you know this thing right here is not quite equal to this. In order to do this trick, you have to already have the derivative of the inside right here, which would be a 5 in this case. There needs to be an extra little piece in there which represents the derivative of the inside. And that's what we call the du. In this case, when you do the substitution, the du is 5 dx. You have to do a little thing, divide by 5 or put a 1/5 in there. There are different ways that people like to talk about this. All right. Anyway, here's the basic, that's the sort of theory behind it. Here's the basic idea of how to do it. Every time you do the u-substitution, you're not really going to think through what I just said, although I'm trying to give you some idea of where it comes from. The way to do it is you choose some kind of inside part of the integral. And this is not an exact science, and there's sometimes when you have to pick the inside part to be something slightly weird. But anyway, to call this u. So in the example that I keep on referring to upstairs, the u is the part inside the parentheses. Usually, if you see parentheses, typically you want to choose the u to be the thing inside of the parentheses. All right? And then you make du equal to the derivative of u times dx. This is how you do the substitution. And then you try to rewrite everything inside the integral. Instead of using x's and dx, you try to rewrite everything using u's and du's. So then you substitute. That's why it's called the substitution. Everything so that all x's and dx's are replaced with u's and du's. All right, this is the basic idea. I'm going to do several examples. There can be sort of easy ones of these and hard ones of these, and we'll try and start with the easy ones, I guess. Let's just try one, and then I have some for you all to try. How about the integral of 2x times x squared plus 10 to the power 6 dx? All right. So the first thing you should do is look at this and try to do it like the easy way without any u substitution. But you should decide immediately that you can't just take the antiderivative directly here, because I have some complicated stuff inside of the power here, this business here, and also multiplication times 2x. That's not something that the fundamental theorem of calculus, doing the antiderivative, you can't just do that directly. If there were a plus here, you might feel better about it, but multiplication, you're gonna have to handle that somehow. And you should do the u substitution in this case. So this involves choosing the u first of all. And I think what makes this harder, it's basically the same as the chain rule done backwards, but what makes it harder is you have to kind of make this choice yourself at the very beginning. There's a chain rule, you just do what you gotta do. There's no choice involved. But here you have to somehow decide for yourself what the u should be. But anyway, I said choose the u to be the inside of something or other. That's the general approach. So I'm going to choose the u to be the inside of the parentheses there, x squared plus 10, not including the 6th power, just the inside part. And then what I say next, choose some inside part to call u, then make du equal derivative of u times dx. All right. So this is all straightforward now. You just say what is the derivative of the u? Can anyone say? 2x. Yes, thank you. And then dx. You always include dx as part of the du in order for the substitution to work out. Sometimes people forget that. If you know what you're doing, you can kind of forget it and still get it, do it right. But if you want to be technically correct, you should put the dx in there. And now the next, I'm trying to follow the steps that I set up here. Make du equal derivative of u times dx. That's what I just did. And then substitute everything so all the x's and dx's are replaced with u's and du's. So over here, my goal at this point is to rewrite everything here, not using x anymore, but using u's as much as possible. And if you know what's up, you can probably do this in one step, but maybe I'll write a couple steps. First, I'm going to just put u where it goes, right? U is the inside here. So I'll just replace that with u. It'll become u to the power 6. And there's some other stuff left over, right? 2x, u to the power 6 dx. All right? Can we replace that other stuff with something involving u's and du's? Well, what's the other stuff here? It's 2x times dx, and sort of by some kind of magic, by some miracle, that actually is the same as du over here. All right? Is that a question?
Would you ever make it 1/2 du equals dx? Like, wouldn't you switch the 2 to a 1/2 behind the du? Or no?
Yes, you could do that if you want to. So there are different ways that people learn how to do this, and if this goes for anything that we do all semester. If you have learned how to do this or that by some slightly different method, you want to do it your way, that's totally fine with me, as long as what you're doing is also correct. I think what you're referring to about dividing a constant or something, that actually is something we're going to do, something like that. Although in this problem, I think it's not entirely necessary because the 2 already exists right here. But anyway, however you want to think this through, you somehow realize that what I'm looking at here is, I have the u to the 6, and then what's left over is 2x dx. And if you write it in this order, now it becomes very clear. I can replace 2x dx, which is here, with du. And so now it says integral u to the 6 du. And I have successfully completed the substitution. That is, now everything is written in terms of u's. There are no x's remaining. And now we can just do the integral. All right? This is a much simpler integral. It's just the 6th power of u. So that integral becomes, 1/7 u to the power 7 plus c, right? This is how we do it. Can I just say a little something about how you write stuff down? I don't know about you folks. Every so often, surely none of you are like this. Every so often I encounter what I refer to as an integral sign hater. I don't know if you're like this. Some people, they just don't like to write the integral sign while they're doing one of these problems. And I say, hey, aren't you like doing the integral? Shouldn't you write the integral sign? And they're like, yeah, I know what I'm doing. Don't worry about it. I got you. I would suggest that you write the integral sign every time. If you're an integral sign hater, you may have forgotten to do this step, right? Like can we just put ourselves in the mind of an integral sign hater? What if you wrote it that way? I would say, what are you doing in this step right here? Oh, I did the integral. Okay, but why? You didn't say you were going to do the integral, and then this equal sign is no longer true. Like, that's not equal to that if there's no integral involved. Anyway, write the integral sign. Come on now. You will end up confusing yourself. And if not, in the best case, you are abusing the equal sign. Anyway, this is pretty much done. There's one final step that we always do at the end of a substitution, and that is to rewrite the answer in terms of the original variable, right? The original question here is about the antiderivative of this function of x. You should write the answer as a function of x. And this step is always easy. It's just you sort of unsubstitute where you see u, you plug that in. So my final answer is 1/7 x squared plus 10 to the power 7 plus c. That's the very last step, is always to replace the original variable instead of u. All right, this is what I would unfortunately call an easy one. There are harder ones in this, but this is the basic kind of u substitution. Anybody have any questions about that? Yeah.
And it's fine in that form. You don't want us to expand it, like to the power.
The 7th power? Oh, definitely not.
Okay.
Yes. Do you want to expand it?
Not really.
No. This would involve like doing the FOIL. This thing times itself 7 times, which don't do that. Yeah. I suppose it's easier if you know Pascal's triangle, but don't even go there. Yes, do not expand that. That's actually, I don't know if you're into expanding things. You actually could have expanded this at the very beginning and then do the integral without the substitution, but you shouldn't do that. It's much harder. Yeah. All right, great. I have a couple more examples, and then I have some for you all to try. This is something we didn't do last time, but I do like doing. Hopefully, every time I will, sort of give you a little example for you all to work on, and I'll sort of walk around and make sure everybody's doing okay. I hope you don't mind me looking over your shoulder. I'm not here to scrutinize you. Here to help. I suppose eventually I am here to scrutinize you, but not today. Let's try. All right, here's a very simple one, or a similar one, but it involves one extra little trick that I know this guy's gonna like. Divide by a number. All right, here's a similar example. It has almost the same format. It has this square root sign rather than a power, but actually this is sort of what you should always do in this class, basically, is rewrite the square root sign as a 1/2 power, because it's almost never useful for our purposes in this class to write things with radical signs. Like so. All right, that's the square root. And now I'm ready to do my substitution. Anybody want to suggest what should I choose for the u? Yes? 1 minus x cubed. Great. Yeah. U, generally speaking, you want to choose to be the inside of something or other. All right. Then the du. The du you don't choose. You calculate the du as the derivative of the u. It should be negative 3x squared dx. All right. And now you should start sort of looking over here. What's going to happen when I plug this stuff in? Well, maybe I'll do this in 2 steps, although you can do all of this in your head if you really want to. First, I just put the u where it goes, in the middle there. And now what's left over is x squared and dx. And if you want to be very clear about it, I find it helpful to sort of gather that stuff together. And you should start looking now. I have x squared dx left over. Hopefully that's the same as the du. If this is going to work out, you want that to be the same as the du. Now in this case, they're not exactly the same. You have a negative 3 as part of the du, but I can make them the same by dividing by the 3 over there. So this is the way that I'm going to always write these. there is a slightly different way that you may be used to working on this, but so what I did there was divide both sides of the equation du equals, this thing. Divide both sides by -3. It now looks like this, and now this is appropriate to plug in directly right here. X squared dx is equal to 1 over -3 du. All right. You may have learned in high school, instead of what I just did, some people like to do something where they multiply by 1/3 and also multiply by 1/3 and also multiply by 3 in order to make the things match. If you want to do it that way, that's totally fine with me. I find the way that I just did slightly easier. But anyway, it works out to the same thing. So x squared dx, when I plug in, is -1/3 du. Right, and then that 1/3, I hope you recall, a constant multiple inside of an integral, you can just pull all the way out to the outside of the integral. So it is 1 over -3 integral u to the 1/2 du. And now the substitution is complete, and we can actually do the integral. All along, we have not yet done the antiderivative. This has all just been a preamble. But anyway, now we can do it. I leave my -1/3 here. Anybody want to say what's the antiderivative of u to the 1/2? Yeah.
2/3 u to the 3/2.
Great. 2/3 u to the 3/2. You are increasing the power by 1. That means 1/2 becomes 3/2. And then you go 1 over the new power. That would be 1 over 3/2, which he writes as 2/3 because that's the reciprocal of 3/2. Excellent. Yeah.
Back before you plugged in the 1 over -3, where did you get the 1/3 from?
Yeah, it came from over here. So in this step, I replaced x squared dx with that. And this 1/3 came because there used to be a 3 over here, and I just divided onto the other side of the equation. Yeah, the goal was to solve for x squared dx because that's what I saw over here. All right, at this point, just to finish it off, this is where the plus c should be introduced because you just did the antiderivative. And then the very last step, we're basically done with the work, but the very last step would be to replace u with whatever it is in terms of x. So it's 1/3, -1/3 times 2/3 times 1 minus x cubed to the 3/2 plus c, like so. And I don't think it's sensible or possible to simplify that anymore. You can multiply 3 and 3 is 9 if you like. -2/9. That other stuff, you can't do anything with it. All right. Excellent. All right. I got, yes, one more sort of simple variation, and then one maybe more complicated kind of hard one, and then I got some for you to try. So one simple thing is, what do you do if you got the little numbers? Like this. If it's a definite integral, can you even do that same thing? The answer is yes. You just kind of have to know. It's not any harder really. You just have to know what to do with the numbers. And there are actually two strategies that people learn in high school. My strategy would be ignore the numbers and plug them in at the very end. So I'm going to say do the integral first. Plug the values at the very end. This is how I'm always going to do it. There's another strategy which involves changing those values in the middle of the problem. You change from x values into u values, and if you want to do it that way, that's totally fine with me. To me, I find it easier to just do everything using the x values and plug them in at the very end. So I am going to just, for now, let's just pretend those numbers don't exist at all. In which case, this looks very similar to the ones that we've already been doing. This, I should say, u is 3x squared plus 5. That's the inside of the parentheses. And then the du would be the derivative of that, which is 6x dx. I'm going to do this a little faster just because it's very much like the ones we just did. Now I plug the u in where it goes. It says integral x times u to the 10 dx, right? Writing in another order, this is u to the 10th times x dx. And what do I do with x times dx? That is basically this, but I have to divide the 6 over to the other side. So this I can write as 1/6 du equals x times dx. And so now I can plug in inside my integral where it says x dx. That's the same as 1/6 du. So it's integral u to the 10 times 1/6 du. Pull the 1/6 out of the integral. 1/6 integral u to the 10 du. And then I do the antiderivative. I got 1/6 and then 1 over 11 u to the 11 plus c. And then finally I replace the x values. 1 over 66. I felt cute, so I multiplied 6 times 11. Sometimes I want to strut a little. To the 11 up there. All right, great. So that's the u-substitution, the standard u-substitution. And now, remember, really, I didn't need to put the plus c because it's my intention to do this definite integral. The definite integral means you do the antiderivative, which is all of that stuff that I just did, and then you just plug in 4 and 1. So now my final answer, so this integral from 1 to 4 of whatever, all that stuff is going to be 1 over 66, 3x squared plus 5 to the power 11, evaluated at 1 and 4, all right? I did the entire u-substitution thing just to find out what the antiderivative is. And that antiderivative, I'm going to plug in 4 and 1 and subtract. So my final answer is 1 over 66, 3 times 4 squared plus 5 to the 11, minus 1 over 66, 3 times 1 squared plus 5 to the 11, like so. This is a times here. All right, that's how we do it. So if you're doing a u-substitution with the little numbers there, the definite integral, you just sort of do the whole thing as if there were no little numbers, and then at the very end, you plug the numbers in. Make sure you don't plug the numbers in prematurely. Like, for instance, right here, you might be tempted, after I did the integral here, plug in 4 and 1 for u. This is not correct. It's because 4 and 1 refer to values of x, not values of u. And this is why the other strategy involves actually changing the values of x into values of u. If you prefer to do it that way, that's fine. Any thoughts about that one? All right, I got one more that's a hard one. I would consider all of these ones so far to be easy ones. I mean, they are mostly routine. They all go kind of the same way. Here's a hard one. Maybe some of you have been feeling all this time, when are we gonna get to the hard ones? How about this? Integral of x times root x plus 1 dx. All right, you may be tempted to say, hey, do you mean x squared on the inside there? If it was an x squared on the inside, this would not be a hard one. The reason that it's hard is it's not an x squared on the inside there. This is slightly weird. Anybody have a suggestion? Yeah?
I'm not sure, but could I just like put it parentheses and then just raise it to the 1/2?
Okay, sure. Yeah, you definitely should do that as a preliminary. Is that any better? Here's something you should not do. This kind of a thing. Can I go x 1/2 plus 1 to the 1/2? Eh? No. That exponents don't work that way. So don't do that. How about this? Can I distribute the x into there? Also no, because the exponent. Actually, you can kind of do that if you turn it into an x squared, but it doesn't help anyway. You get another weird looking thing. Any other ideas? You can still do a substitution. So if I tell you ahead of time that the substitution is how you're supposed to do this, what are you going to make the u? In my opinion, there aren't very many options, right? How about x? I suppose your choices are x or x plus 1. It turns out making u equal x never does anything. Like, the whole idea of the substitution is to change the variable into something else. So you don't change x, make u equal x, never does anything. I'm going to go u equals x plus 1. Even though it's not clear that this is going to do anything, but let's just try it out. What is the du then?
dx.
Yeah, 1 dx, right? It's the derivative of u, which in this case is 1, and then times dx. Okay, so I can try to plug everything in. So this equals, okay, I have x. I don't know what to do with x, but anyway, x plus 1 is u. So this is times u to the 1/2. And then dx is the same as du. So, all right, that's a du there. What are we going to do with the x? Here's the sweet tricks, or the tricky trick. Anybody see what can be done with x? Just x. Yeah.
This might be wrong. Is it a constant, so you take it out?
No, the x, yeah, it's not a constant. Because, this is x inside of an integral. X definitely, if x were a constant, you would have just taken that at the very beginning, which is not an idea.
Do you make it in two integrals?
No, this is not, yeah, you may be tempted to say, let's just like split it up into, yeah, this guy and this guy. That's not allowed when it's multiplication. If it was addition, you could do that, but what do you think?
You just like re-solve u equals x plus 1.
Mm-hmm. Yeah, what do you mean by that?
Like x is equal to u minus 1.
Yeah, this is the weird step. In the other examples, you never had to do something like that, but sometimes you do. In a hard one, x equals u minus 1. Is that actually helpful? All right, let's try it out. X, I put u minus 1 here, and then u to the 1/2 du. From a certain point of view, this doesn't look any better than what I started with. The whole point of this is to make it simpler. Does anybody have actually, that is simpler. Anybody see why? Yeah?
You can distribute.
Yeah, this you can now distribute. Why didn't we distribute at the very beginning? Like right here, it's because the exponent messes it up. But now the exponent is kind of on the other one, and you can distribute. This is strange, but it works out great. So what do we get when we distribute? It's going to be, so I'm doing this kind of thing. U times u to the 1/2, what would that be? U to the 3/2, yeah, because you add the exponents, and then minus u to the 1/2 du. And can you do this integral? Yeah, it's added together or subtracted, whatever. And so you can just do each one separately. So I go, this is u to the 5/2, 1/5, minus u to the 3/2, 1/3, plus c. That's the end of the hard stuff. And then, as always, the very last step is replace all the u's by x's. So our original substitution was here, u equals x plus 1. So these u's become x plus 1s. And we're done. If you like, I'll write these reciprocals. 2/5 x plus 1 to the 5/2 minus 2/3 x plus 1 to the 3/2 plus c. There you go. Wild and crazy. This is the hard one. So sometimes you have to do some sort of extra little weird step. In this case, it was this bit right here. It's kind of a non-standard step in a u-substitution. All right. All right, we got 15 minutes left. I think that's enough time for you all to try some. So like I said, I'm going to give you a few. Please feel free to chat with your neighbors about it. See what you got. The first two are sort of, I would say, easier type ones, and then the last one is a little trickier. That's the integral from 0 to root pi, x times sine of x squared. Next. And finally. All right, see what you think. Like I said, I'm going to walk around and see how you're doing. I'm not going to collect these or give you a grade or anything like that. I'm just trying to make sure that you guys are with it, and I'm here to help. So I'll give you about 10 minutes, and then we'll talk about these. I don't know if that's enough time to actually do them all, but that's okay. Should start by choosing the u. Something inside of something.
just like this, 10 becomes 11, so you go remember that here it's 3 halves. Yeah, it's just 5 halves. All right.
How are you?
All right.
Because it's
You okay?
cosine
Good.
square.
Yes. Yes.
So when you do this,
You good here?
cosine u. That's like 1/2 times cosine square. And when you plug in x,
You
it's square root of x. Oh, the integral of sine is cosine negative
You okay?
because the derivative
Doing good here?
of sine x is
Just, yeah, you wanna choose just the. Is that? What you wrote projection around.
okay, so when you negative 1/2 cosine
Alright.
u. What's your u? Okay, so
Alright.
substitute x squared.
Actually, there should be one. So you have. X u is 2x, which is the x there. And then to actually get x is 0.
Cosine pi is or
Alright.
negative 1. Cosine pi.
Because then you plug in 1 times
Cosine pi is negative 1.
Alright. So you said, yeah, this, the fact that it's squared here is weird. I just don't like it. Like I draw.
Oh,
No, it's just, it's, when you do this, you know it's x squared. This x squared is one.
minus.
This is 0. So there's all this time. If you really want to do squared, then you have to process it.
I got 0.
You guys doing okay?
Because negative.
Second one? I got 190 times 190 times parentheses 1 plus x cubed to the negative third power plus c.
Doing okay?
Like,
So it says this 1/2, it changes back to 0 to pi, right?
yeah.
You good here?
So kind of like this, but
Yeah, or change to x squared.
oh yeah.
And then I want and then I just subtract it like cosine, I think it's 1 minus 1. I don't know if that's right, but that's the second one.
Yeah, so, yeah, and you should put a dx here.
It ends up
Dx
being,
will-
it ends up being positive.
Oh yeah.
Here for the first one.
Wait, so what's
But yeah.
cosine is 0?
So over here, I don't see it.
One half.
That's
Oh,
what
one.
but I do see an x.
Wait, let me see. Put it like, and then this one.
Yep, so you get 0. That's right.
This one.
Cosine of pi is negative.
Yeah, this is
Yeah,
one.
so instead of x is 1
Yeah.
plus, we have 1
So it'll be 1/2.
There's a way to do it.
One's negative 1.
So then it's plus, no, because then you dropped your x there. Because you say plus.
And usually I would write this as.
Wait, so what's cosine? What's cosine pi? Cosine pi is negative. Negative. So I got negative 1. I got negative half.
But you should here, get negative cosine times negative multiply by 2. This is multiply by 2.
Yeah, then it's
Yeah,
negative 1 half minus negative 1, so that will be positive 1 minus 1 half.
Then it's minus negative 1.
sure cosine of zero. As a rule, minus the negative cosine. Yeah, but it's 1/2. This is
No, it's not.
over 2. Memorized.
You got Cuba, so.
And then there's this one. Yeah, and then
I don't think you guys have to modify that part. You can literally leave it as cosine -1, right?
You're on the third.
So you
Oh, yeah, so.
You get X cubed from X squared.
Yeah,
I have to be like on both
Oh wait, did I not?
No, you're right, yeah.
Well, it's like.
I know, because you're talking about the one, but you're adding.
I think it's on the website, so.
The last one.
And then with the 1/2.
Oh, shoot, alright.
Maybe it's on his website.
DX thing.
What do you choose for
No, but
Cuba?
when you do this step,
Plus 1, but
you change the sign to negative.
when you do that, you get, it doesn't cancel out.
Like simplifying that all the way to the first one.
No, I think
Like,
I
other than like,
choose
other
X
than
cubed.
finding like the cosine value.
So I think you would have
I think it's my first time.
Yeah.
So first put next
So.
Or maybe you choose it, because then you get 3x.
And then the next square and cancel out.
Oh, you can't cancel out.
Yeah. Dude, I went up to Cal 2 in high school, like I took PC, and then I got my realty exam, and then I took it at my old school.
All right, we got to go soon, so I want to go over these. Sorry I didn't make it around to everybody twice, but people seem to be doing all right for the most part. So the first one here, you should do u equals x squared, and then du is 2x dx, and then divide the 2 will come up 1/2 du equals x dx. All right, and these are the things that I'm going to plug in over here. So just plugging the u in first, it'll say x times sine of u dx. But if I sort of gather the x's together like I like to, it'll say sine of u times x dx. And then x dx from here is 1/2 du. So this will say integral sine of u times 1/2 du. And we pull the constant of 1/2 all the way outside the integral. 1/2 integral sine of u du. All right, that's the u substitution is complete. Now you have to actually do the integral, which turns it into 1/2 sine. The integral of sine is negative cosine, so when you do this integral, you introduce a minus sign. This is ordinarily where I'd put the plus c, but I'm going to plug values in anyway, so the plus c is not relevant. Next, I replace u with x, cosine of x squared. And this I'm going to evaluate at the two values of 0 and root pi. I hope everybody got something like that. Yep. This du here, it disappeared when I went down there, right? What happened to it is it disappeared. We're talking over here, folks. Thanks for trying to help out. The du always disappears when you do the integral. This may seem jarring to you. Shouldn't I do something with the du? The answer is no, it straight up goes away. This is because, for example, if I ask you what is the integral of x squared dx, the answer is 1/3 x cubed. You might say, what happened to the dx? Where did that go? Well, it goes away when you do the integral. That's just sort of how the notation works. The integral sign and the d whatever, they always go away when you do the antiderivative. It's confusing. Usually you think of this dx doesn't really mean anything. This du kind of feels like it means something and you don't want to throw it away, but you should throw it away. All right, finally I'm going to plug in the two values. We got minus a half cosine of root pi squared, of course it's just pi, and then minus a half cosine of 0 squared. And cosine of pi is 0, cosine of 0 is 1, sorry, cosine of pi is minus 1. So this ends up being plus 1/2, and then this is a plus, you get another plus 1/2, and the answer is 1. I'm trying to do this a little fast just so that we can get through them. Any questions about that one? I saw most people as I was walking around got this one all right. It's a little tricky, but okay, great. The next one. This one is slightly harder again. Let me put this guy away for now. This one, what do you think? What did you choose for the u? Anybody who worked it out? Yeah?
1 minus x cubed.
Great. Yeah, if you see parentheses with something inside the parentheses, probably that's what you want to pick to be the u. If you see a fraction, generally the u comes from the denominator rather than the numerator, although that's not a law or anything. Anyway, the du is negative 3x squared dx. And as I usually do, I'm going to divide that extra constant. In the previous one, I divided both sides by 2. Here I'm going to divide by negative 3. I write it as negative 1/3 du equals x squared dx. And I'm beginning to feel good about this because this x squared dx, I do see sort of over here, x squared times dx. If you don't see anything like that, then you should begin to feel nervous at this point, but I'm feeling pretty good so far. All right, so let's plug everything in. First, I'm just going to put the u where it goes, which is in the denominator. This is u to the 4, and I still have x squared and dx. But x squared and dx written together equals this thing, negative 1/3 du. I think the easiest way, if you want to write up, maybe you can do all this in your head, which is fine, but if you want to write out intermediate steps, rather than dividing by u to the 4, I'll write this as multiplying u to the minus 4. So this is the same as u to the minus 4 times x squared dx. So this is one of your old algebra simplifying tricks. This is what I meant when I said yesterday, this class is not about simplifying, so I'm not going to make you simplify your answers, but you're going to have to do some simplifying in between along the way. All right, anyway, x squared dx is negative 1/3 du. So this, pull the negative 1/3 out, negative 1/3 u to the minus 4 du. And then we do the integral. It becomes 1 over minus, sorry, adding 1 in the exponent is negative 3, like so, right? And then I replace the x's. U is 1 minus x cubed. So this all makes 1/9 here, and then 1 minus x cubed to the minus 3 plus c. There you go. All right, and maybe, do we have time to do the last one? I think we have time to do the last one. Unless there are questions about this one? If you can ask me a 2-minute question about this one, then we won't have enough time. All right, let's talk about the last one. The last one was this here. This is what I call a hard one, although it's really the same trick as the other hard one that I did. So if you had enough time to look back at your notes, you would have seen a similar trick. So here I, again, choose the inside of the parentheses. The du then is 2x dx. And as usual, I'm going to divide the 2 across there and say 1/2 du equals x times dx. Now going back to try to plug this stuff in here, it says x cubed u to the 10 dx. And now the question is, what am I going to do with x cubed? Did anybody work this one out? Yeah?
I made it into x times x squared.
Yeah. This is a non-obvious trick, but it's certainly true. You can sort of leave a x squared here and then put another x together with the dx part. I think this is a weird step because it's not obvious that you should do that, although I hope you agree it's certainly true. I took an x cubed and split it apart into x squared and x. The reason that you might think of doing this is just because you want to see x times dx. So you can make that happen here. You just have an x squared left over. All right. Anyway, this then becomes x squared times u to the 10 times 1/2 du. What did you do with the x squared?
I subtracted the 1 from the u, so it's u minus 1 equals
Right.
x squared.
X squared is u minus 1. So this becomes integral u minus 1 times u to the 10. Let's pull the 1/2 out, like so. And then to finish, sorry, I can finish in a minute. We distribute the u, right? U to the 10, I mean. Distribute the u to the 10 like so. So it becomes 1/2 integral u to the 11 minus u to the 10 du. And that is now an easy integral to do. Sorry to do this so fast. 1/12 u to the 12 minus 1/11 u to the 11 plus c. And then finally we replace the x's, and that's it. U was x squared plus 1. So my final answer, 1/12 x squared plus 1 to the 12 minus 1/11 x squared plus 1 to the 11. All right, that's a hard one. You'll have some more practice with these on the homework, and I would be happy to sit down and go through them if anybody's feeling a little shaky.